Good morning, students. We're going to do day 55, properties of the definite integral. Some of this is sort of common sense. It's the same kind of properties that we use with derivatives. The constants being able to be factored out. You can break apart a function and do the derivative of each term separately. You can do the same thing with integrals. So it's kind of like this. I need to wrap this up because there's a quiz scheduled afterwards. So, my goal for the quiz up through this material will be probably Thursday. I will also be lecturing about using the antiderivative to solve some problems having to deal with distance and position of objects. So, I'll get that done this week also. Then you'll have a long 4-day weekend, which you deserve. Okay? Let's get this started. Day 55. I just realized they never ever label the lecture part. They lecture, edit these documents for next year. All right. Quicker I get started, the quicker I get done, the quicker I quit bothering you. Notice we have a lower limit and upper limit. We're doing the derivative as we go from A to A. Let me just share a picture with you. If this was a function going from A, and I'm going to find the area under the curve from A, and I go as far over as A. I'm going to zoom in. How much area did I get? Well, this line is microscopic. So I've only done the area up to that line. So the answer is 0. I can prove it to you. Right over there. The integral from A to A will be the antiderivative f of x from A to A, which will be equal to, plug in the top value, minus plug in the bottom value, 0. Boy, I was brain surgery there. Now, given that the lower limit is less than the upper limit, and C's in between, and we know for a fact that if I'm integrating from A to B, but there's a C in here, and I want the area between A to B, and I know C's in the middle, I want you to realize, if it's necessary, you could break it up and go from A to C and add that area from C to B. So that means that equals to the area from A to C of f of x dx plus the integral from from C to B of f of x dx. In other words, you can break f of x apart using the limit. As long as this is continuous and differentiable and all those things we've talked about before. I think there was a homework problem or a lecture problem that I did not see that the C in the middle wasn't defined, so that was a problem. And it isn't even the fact that it has to be differentiable, it has to be continuous for sure. And I guess and differentiable because going towards an asymptote, still continuous. It's just can't take a derivative there. Unless someone corrects me, I think that's pretty good. Look, if we're going from A to B, and we know that the answer is K. We already know the answer to the integral. That meant this. A to B, area under the curve, is K. So we already calculated it. We already have done the answer. We've already integrated. I better should label this as f of x. We've already integrated f of x from A to B, and we got the answer of K. If that's true, now look at my limits. A is typically to the left of B. That's how we integrate from left to right. But if you changed it from right to left, then the answer would be the opposite area. It's a really hard thing to think about. But when you go this way, the area turns to negative K. So sometimes we switch it on purpose just because we want to flip it. What if the original area was left to right? Then we can switch it from right to left and switch the sign. That's why it's a property. Given that B is less than A, could we go A to B? Given that B, or he switched it. Yeah, that's what he just did. If B is less than A, and he's going from A to B, since it's the opposite direction, whatever that original area was, the area is going to be opposite of, if B is less than A, B to A of f of x. If I switch the limits, I switch the sign. If k is a constant, and I'm integrating from A to B, and k is multiplied by the constant, that's no different than integrating 2x squared dx. In other words, I could factor out the 2 first and integrate this as 2x to the cubed over 3. I didn't put limits, so it's just still plus c. This one has limits. So I factor out k, and I integrate from A to B of f of x dx. That's all it is. If you don't want to mess with the constant, pull it out. What if I have 2 separate functions? That's no different than this. Integrate 3x cubed minus sine of x dx equals to integrate 3x cubed dx minus integrate sine of x dx. That's all we're doing, is breaking the terms apart. You're integrating 3x squared plus 2x minus 5 dx. You're doing it one term at a time anyway. Each of these get their own special integral sandwich. So it's integrating from a to b of f of x dx, plus or minus, doesn't matter what the symbol was. Integrate a to b of g of x dx. Terminology, what does it mean for a function to be even? A function is even is if you take f of a and you plug in f of a negative a and you get the exact same image. In other words, symmetry on the y-axis, f of a is equal to f of negative a. That y values are the same. That's even. Interesting about being even. Here I'm going from negative a to a. I want that area bounded underneath us here. I want this area from negative a to a, but since it's a reflection, I could have just broke it up into 0 just to the positive a, and guess what? Multiply it by 2. It's the same thing. Start at 0, just take that piece and times it by 2. We use that all the time. It's really handy. Odd function. Let's review your odd function terminology. Odd function is f of a is equal to negative f of a. I should say that's not true. That's not true. That's not equal. What happens is f of a is f of a, but f of a negative a is equal to negative f of a. Because what happens if this is a, there's my f of a. Take the opposite of a, and notice down here, negative f of a. But there's something interesting. It also meant that when you rotated this object around the origin, it's symmetry on the origin, that you could rotate this upper piece, this curve becomes this curve. So it has symmetry on the origin. And the ironic thing is, this area is really the same amount as this area, except I will say this area I'm going to call K for being positive area. This area is underneath the x-axis. What's negative K? So the area from negative A to A ends up canceling out because they're the same areas. When you add them together, cancels out. That was special. When I get done, note to self. All right, we can use these ideas if we already know the answer to an integration problem of a particular component. So in your mind, you're looking at two areas, and I'm just going to simulate something happening here. 0 all the way to, okay, I see something he did. Let me modify my picture, because I wasn't really paying attention to that. 0 to 3 had an area above the curve of a positive 6. Then 3 to 7 has area under the curve of a negative 8. So for these problems, that's a fact, okay, till I change it. So I'm looking, if I know from 0 to 3 was 6, then 3 to 0 is the opposite direction, would have to be the opposite of 6. If I know 0 to 7, one component that I broke up was 6 and one's a negative 8, then technically this is the same thing as 0 to 3 of f of x dx plus 3 to 7 of f of x dx. That gave me the 6 plus a negative 8. Resulting area, net area is a negative 2. Okay, lost my picture up there though, so maybe you can still see it. 0 to 3 and 3 to 7. We've talked about this problem before. If I'm going from 0 to 3, that's one thing. But if I stay at 3 and go to 3, I haven't done nothing. 0. This was 3 to 7. If you remember, 3 to 7 was a negative 8 area. I'm just using this as my x-axis. And I'm going the opposite direction. Well, that's sometimes why we switch it around. 3 to 7 of f of x dx was a negative 8. If I switch it from 7 to 3, then the sign switches to a positive area. That's the problem we were just doing. Oh, I didn't see the 3. Hold on here. That's true. I'm not lying. I didn't lie. If I take 3 times my 7 to 3, of f of x dx, that gives me 3 times a negative 8, negative 24. Okay, that was a close one. Got to pay attention, Cartwright. Pay attention. Okay, this obviously is you're dealing with one term, two term, constant in front. So let's put it all together. Equals to the integral from 3 to 7 of a 2 dx plus the integral from 3 to 7 of a 3 outside f of x dx. Now, if you have a constant of a 2, reminder what that looks like. It's a constant. It's a horizontal line. And if we're going from 3 to 7, and you want the area under the curve underneath the 2, then obviously it was this rectangle from 3 to 7, which is a 4, and the height is a 2. I know that the answer of that rectangle, change my marker to black, will be 8. It's just a number. It's just a constant. But when you work it out, it looks like this. You have the 2, and it's really an x to the 0 power, so it becomes x to the 1 power divided by 1 from 3 to 7 plus the antiderivative of f times a 3 to 7. So plug in the top number, 2 times 7 minus 2 times, oh, I'm thinking of my answer. 2 times 3 plus 3 times the answer of f of x from 3 to 7, which was a negative 8. As I recall, up here, 3 to 7 was a negative 8. That's what he gave me right here. So 2 times 7 is 14, minus 2 times 3 is 6. Do you notice there's my 8? Told you it's going to be 8. You didn't believe me. Plus 3 times the negative 8 is a negative 24, negative 16. Now he said here, negative 3 to 3 of f of x if we know f of x was even. See, we don't have negative 3 to 3. The problem is, in my picture, I have no idea what it looks like at negative 3. Except for the fact he did give me a secret right now. He told me it's an even function. So whatever picture I had here is technically the same image over here. So I kind of do know that from 0 to negative 3 had to be the same picture as this. So if that was 6, this had to be 6. So here's what I'm going to do here. I could break that up into 2 integrals from negative 3 to 0 of f of x dx, add it to 0 to 3 of f of x dx. And that meant they both have the same areas. So negative 3, 0 to 3 was a 6. So this had to be a 6. Give me an answer of 12. Or you could have done 2 times the area between 0 to 3 of f of x, which is 2 times the 6. 12 was 6, right? Yes, it was 6 right there. I forget. Last one. It's an odd function. So that all I can say is if I thought that it looked like this thing here, and it's an odd function, if I rotate this around, rotate it around, it's going to give me this picture here. So what you're supposed to realize that you break that up into 2. If you integrate from negative 3 to 0 of f of x dx, and you add that to the 0 to 3 of f of x dx, and we knew that 0 to 3 was 6, then we knew this had to be a negative 6, just because one area was a positive 6, that area had to be a negative 6 because it's underneath the axis. That goes to 0. Don't know why he didn't put another problem here to finish up that spot. Lecturing using a graph picture. What is the value from 0 to 3? 0 to 3. What do you see? It's a composite geometry figure. You see a quarter circle, and some people see a rectangle and a triangle. Who am I to begrudge you? But I'm sort of a trapezoidal man. I see a trapezoid. So I also see symmetry on the y-axis. I see the other part of the quarter circle. And I do see another trapezoid. Or, if you wish, another rectangle and a triangle. I'm going to do trapezoid. So what I'm going to do up front, since I know we're dealing with geometric shapes and everything here is above the axis except for this triangle here and this triangle here, which might be the same area as one of these triangles. So I might want to see all the areas of every piece before I get started. That way you can catch any of my mistakes. From -3 to 4, that distance is a 1. And it's actually, if you want to think about it, it doesn't matter if you go from -4 to 3, -3 to 4, it's still a 1. The height goes down to a 1. So from 0, that's a 1. So that triangle, that area, is base times height divided by 2. 1 times 1 divided by 2, 1/2. But it's underneath the axis, so it's a -1/2. Let's check this triangle here, just because. I may need it. I'm still going to treat that as a trapezoid, but nonetheless. Well, while I'm at it, I guess I'll do rectangles now. I changed my mind. That's a 1. That's a 1. So, and it is going to be a 1 times 1 divided by 2. That becomes a +1/2. So I have a -1/2, +1/2. Rectangle, 2 by 1. That area is 2. Oh, that meant the trapezoid was 2.5, 2.5. So may as well be consistent now. 2, boom, boom. 1 by 1, 1/2. Quarter circle, that's the radius. It's a distance of 2. Distance of 2. So it doesn't matter which way I go, it's a distance of 2. Area of a circle is pi r squared. Pi times 2 squared is 4. 4 pi. But each piece is a quarter of it. So I really need 1/4 of the area, which is just pi. In other words, half a circle has an area of 2 pi, so that's a pi. That's a pi. Now, I do this because it's worth your time. Distance of 1 underneath the axis, -1/2. I do this first because it saves me a lot of thinking. What is the value from 0 to 3 of this picture? 0 to 3 implied all the area you see from 0 to 3. So that tells me it's a quarter circle plus a rectangle plus a trapezoid. Quarter circle. That was a pi. Now, I'm going to put approximately, well, for sure, I'm pretty confident for this one. It's a pi plus a rectangle. This was the quarter circle. This is the rectangle, 2. And this was plus the triangle, which was a -1/2. So the best way to write this would be pi plus 3/2. because 2 minus a half is 1.5. What's the value from 0 to 4? 0, that's what this problem is, 0 to 4. Oh, I messed up. That triangle was not negative. I think I just did this answer. Not actually. Actually, that's going to cancel out. This was a positive pi. Positive half, I mean. So it's pi. Well, that's kind of interesting. All I got to do is change this to a 5/2. Okay. Now you'll never know I messed up. All right, if I'm going from 0 to 4, it's the previous answer minus that triangle. Just in case you don't see it, it's going to be the quarter circle plus the rectangle plus the triangle minus the triangle. That one down there. So these two triangles we already said were the same. They canceled out. So my answer is really going to be pi plus 2. Negative 3 to 3. Well, we've already done 0 to 3. 0 to 3 was the pi plus the 2 plus the half. So this would just be 2 times the 0 to 3 of f of x dx. And that'd be 2 times, wasn't it 5/2? 2 plus pi, 2, well, pi plus 2 plus a half was pi plus 5/2. You could leave that or call it 2 pi plus 5. If f of 0 is 5, now don't get hung up on what the picture is. It says if. It's purely hypothetical. If the answer at the start of 0 is 5, he's telling me that when I started, that's called like an initial position. It's a constant. Then what's the value of f of 3? Go back up to my picture. Let's look up here. Well, no, let me just set up my integral first. F of 3. Let's set up my f of 3, because we want. F of 3 means the integral from 0 to 3 of f of x. We know that if we apply the rules of the antiderivative, it's the antiderivative of f of 3 minus the antiderivative evaluated at 0. Well, we already did this answer. It was right up here. And it was the area all that area. So we did it already. So that stood for pi plus 5/2. And it's equal to f of 3, which is what I'm looking for, minus f of 0. Well, f of 0 doesn't mean a whole lot. I can't go to the picture and find f of 0. It was a starting place at 0. I had no idea what f of 0 was. But he gave it to me here. So pi plus 5 halves. I'm looking for f of 3, and I'm going to subtract what he told me f of 0 was, 5. Solve this for f of 3. F of 3 will equal to pi plus 5 halves plus 5, which is pi plus 5 halves plus 10 halves, which is pi plus 15 halves, which is 7.5 if you choose to do it. I'm going to leave it as 15 halves. If f of a negative 2 is a negative 2, so if I go back to my picture, f of a negative 2, he's giving me another starting place. So hold on to that. What's the value of f of 2? Well, we know, again, that if we're going to integrate I don't want to do 0. I want to go to negative 2. The reason I'm picking these values is because negative 2 and 2 are the values that are mentioned in here. Those are limits. So I'll put the small one down here, of f of x will equal to, the definition will be big F of 2. You see why I put the 2 as a limit? Because that's something I'm looking for. Minus the antiderivative of a negative 2. The reason I put that as my lower limit, because that's something he gave me. Now, technically, all of this is doable from our picture. From negative 2 to 2. We can get that answer. It's 2 quarter circles and 2 rectangles. From negative 2 to 2. So it's a pi plus a pi is 2 pi plus 4. So the answer to this part right here is 2 pi plus the 4 will equal to what I'm looking for, f of 2, minus what he gave me as a negative 2. So that's 2 pi plus 4 equals big F of 2 plus 2. Subtract 2 from both sides. 2 pi plus 2 equals to what we're looking for, f of 2. Or was it f of 2? F of 2. Yeah, I can't read my handwriting. 2 pi plus 2. So those are the trickiest ones. Notes. Next page is a free response problem. This actually came up in 2003. So you see what you have? It's just like the one we just did. You have regions, you have areas, area. This is the hard area. Would love to challenge you to define what each of those regions would be bounded by the x-axis. If you have any questions, you can shoot me a question on this. And this is going to be this problem is going to be a mixture probably of derivatives and integrals. Challenge yourself. Challenge, be a good test question. This is the kind of question I can see that the AP would throw at you this year, because you're only going to get 2 free response problems. And here's a free response problem that has a lot of stuff we've been doing. Challenge yourself before you look up the answer. They do label the homework, but they never put it on the lecture. And there's day 55 homework. So Guess I'll catch you on the flip side.